So you might have seen our last attempt at making a heat sink, where we took a reciprocating saw to a block of aluminum with what could best be described as limited success. But of course, persistence is the name of the game here at LMG, so we went through the YouTube comments, which were full of suggestions about casting our own heatsink from molten aluminum, and decided to set about doing it. But is that really the kind of thing that you can do with $100 worth of supplies and an empty warehouse? Well, there's only one way to know for sure. So casting then, I guess we'll need a couch to, haha, no. We're talking about the kind of casting where a molten material is poured into a mold so that it solidifies in the desired shape. There are a couple of important elements that you need. A foam or plastic replica of the intended finished design, and a material that you can mold around it that can hold its shape. The primary design considerations for our heatsink were how easy it would be to cast and how much heat it could dissipate. We kept it as simple as possible in SolidWorks, with the two pieces coming off the heatsink being to allow for the metal to be poured into one end and the gases to vent out of the other. And the mold had to be orientated in such a way that the bottom would be the most likely surface to have a smooth, flat finish. Although the fins ended up thicker than we'd have liked, when it comes to heatsinks, size matters, and we calculated a theoretical heat dissipation of over 200 watts. So then, we went ahead and printed our design using PLA plastic at 103% size to account for the shrinkage of the aluminum during cooling. We chose PLA because it's made from corn, so when it burns, it shouldn't poison us. To improve our odds of success, we needed casting-grade aluminum. But buying that stuff new is pretty expensive. Fortunately, there's a large source of casting-grade aluminum, the scrapyard. So we headed there and picked out our victim, extracting the engine out of this 2002 Toyota Yaris. Back in the shop, we took apart the engine, cleaned off the dirt, and chopped it into pieces small enough to melt. We used foam then to extend our pouring and venting holes. Then we mixed up clay, sand, and water until it reached a consistency where it was pliable, but able to hold its shape. This mixture, called green sand, was packed around the 3D print and then baked for a couple of minutes to partially melt the plastic and to harden the clay. This whole process is called lost PLA casting. We then placed the aluminum scraps that we had into a graphite crucible, which is basically a large cup that can withstand really high temperatures, and set about melting the metal in a crude furnace that we made out of fire bricks. One of the best and worst things about aluminum is that when it's exposed to air, it almost immediately forms an aluminum oxide layer on the surface. This is good for preventing further corrosion, but it makes it very annoying for melting. So it's important when casting then to remove the aluminum oxide layer that floats to the top, called dross, so that it doesn't contaminate the finished cast. With the dross removed, we were ready for our first pouring attempt. Though it should be noted, we weren't sure how much of the PLA had actually melted on this one. Turns out, not much. Clearly, the aluminum barely made it into the mold and wasn't able to melt much of the plastic in the process. So to troubleshoot then, we made a different riser design out of foam so that the aluminum would be able to enter across the entire top of the mold. Green sand, melt, purify, and pour again, and we ended up, once more, with a face only a mother could love. So we moved on then from lost PLA casting to lost foam casting, which is an extremely popular and much easier way of creating molds. Due to the low melting point of foam, when the aluminum is poured in, it immediately melts it away and fills the space, in theory. Our foam mold wasn't perfect by any means, but we were cautiously optimistic that it would work. So fire, melt, and pour again, and we get to see what kind of a result we were going to get. And unfortunately, this wasn't a massive success either. Although the foam did melt away, and we were able to create a good base layer, and even where the mounting plate would be was fairly well done, we simply didn't have enough static pressure to force the molten metal up into the fin shapes. We could solve this by creating a much taller riser, but by this point, the time crunch had become real, and our engineering department realized that he needed to produce something usable or I might melt him down. So he made a clay and fire brick sandwich and assembled a mold using a method that bears more resemblance to grade 1 art class than to precision crafting. To ensure on this, the final attempt, that the metal would thoroughly melt, the furnace was remade and heated until the entire crucible was red hot. Upon pouring the aluminum into the mold, it started bubbling from the steam escaping from the clay, making the metal of the finished product more porous, a problem we hadn't had before when we were using green sand. So then, with a bit of massaging from the reciprocating saw to make it fit on a motherboard, it was finally ready to mount. The processor chosen was an Intel Q6600, mainly because the old Asus motherboard it was on was the only one where the heatsink didn't interfere with the VRM, and to help fill in the air pockets on the bottom of the heatsink, we added a more than generous dollop of thermal paste, topping off the creation with a handful of zip ties. And this was actually the first time I laid eyes on what 3 of my staff had been doing all week. I don't know how anything could have been worse than what I was expecting, but this may have achieved it. I mean, the name of the series is Sketchy Heat Sinks, and I guess mission accomplished there. With all of that said, testing an IDA 64 turned out better than expected, and Sketchy Heatsink number 2 was able to keep the CPU reasonably cool for a fairly long time, although this is likely more to do with its large thermal mass than its ability to dissipate heat. Ambitious, but rubbish. 10 out of 10, IGN. So yeah, in the end, this turned out to be the no man's sky of heatsinks. Sure, we had high goals set, and we believed with the resources we had, we could pull it off, but it took 3 times longer than originally planned, and the end result performs poorly, looks bad, and has almost none of the features that we said it would have in the beginning. So then all that's left to say is thanks in advance to the metalworking experts who by now have filled the comments with advice. We will bear it in mind for the next installment then of Sketchy Heat Sinks. So thanks for watching, guys. If you disliked this video, hit the dislike button, but come on, where's your sense of fun? But if you liked it, hit the like button, get subscribed, maybe consider checking out where to buy the stuff we featured. I mean, what would that even be? Like, scrap aluminum? At the link in the video description, and also the link to our community forum and our merch store, which has cool t-shirts just like this one.